This little wafer contains photosensitive pixels, made with a semiconductor that is fabricated from copper. And I'm not gonna lie, this wafer has totally kicked my butt. Results have been, at times, exciting.
This does that. Look at that.
And at times, pretty discouraging.
That's a week's worth of work down the drain, and I get to start over again, which is just great.
And more than a few times, I've accidentally blown up what I was testing.
Oh, it went.
This will probably be a long one, so buckle up. Today we're talking about DIY semiconductors. To make advanced electronics and light-sensitive devices, you need a semiconducting material. And while silicon is obviously the most popular semiconductor, it's not the only one. There are dozens of different semiconducting materials out there, being studied for a whole variety of reasons. But the one I'm most interested in is copper oxide, the oxidized state of plain old copper. Copper oxide is a p-type semiconductor with a direct band gap of 1.2 electron volts. We don't need to get into exactly what that means, but what you should know is that it's sensitive to visible light. Visible light photons have enough energy that they can knock electrons loose inside the material, which in turn generates an electrical current. This is the basis of a photovoltaic cell, basically a solar cell. So copper oxide allows us to build photosensitive sites on a wafer. And if we wire those up with electrodes, we can build a little camera with light-sensitive pixels. This will be a good test of both the semiconducting layer and the necessary extra bits like depositing electrodes and probing the resulting circuit. To actually grow the oxide, I'm following a thermal oxidation protocol from this Nature paper. First, we take a silicon substrate and grow a thick layer of silicon dioxide on top, which is done at 1,000 degrees in a furnace. We need to grow this oxide so that there is a physical barrier between the experiment and the underlying silicon. It would be pretty silly to go through all this effort to make a copper oxide device and then realize we were actually measuring the silicon substrate instead. We could, of course, just use a different substrate and skip all of this initial prep. But silicon is just convenient. It's very flat, relatively cheap, and the insulating oxide is easy enough to grow. Next, we deposit a thin layer of copper on top using magnetron sputtering. I'm depositing 80 nanometers of copper for all of my tests. Then, we oxidize the copper to make our semiconductor. This is where it starts to get a little complicated. So far, I've been saying copper oxide, but there are actually two different types. There's copper 1 oxide, also known as cuprous oxide, which has this formula. And then there's copper 2 oxide, also known as cupric oxide, having this formula. We're mostly interested in copper 2 oxide. Copper 1 is also a semiconductor, but has a larger band gap, around 2.1 electron volts, which means it's not quite as sensitive to visible light. If you heat copper up to around 200 degrees Celsius, you'll mostly generate that copper 1 oxide. But as the temperature increases, you'll convert that copper 1 into copper 2. So we put our sample inside the furnace and crank it up to 700 degrees Celsius and leave it there for an hour, which is where the first problem started to happen. My tube furnace just has an analog control method, and if you're not careful, the temperature can kind of fluctuate and swing. If the temp swings a bit too high, the oxide has a tendency to ball up and form these geometric patterns. It's actually really beautiful to look at, but it's entirely useless. As an aside, I think these geometric patterns are due to the copper oxide following the underlying crystal orientation of the silicon, which is, not gonna lie, it's pretty cool, but it's also, not at all usable. So we have to rerun the experiment, but keep a better eye on temperature and try to err on the side of cooler. So I completely forgot to mention the adhesion problems that I ran into. The original paper makes a note of this in the methods. It says, quote, "A strip array configuration of copper is patterned for the sensing film to alleviate the adhesion problem during the following high temperature annealing process." Basically, they used thin, narrow strips of copper oxide instead of a continuous film because the smaller surface area has less internal stress, and so it's less likely to peel off. And I definitely found this to be a problem. If you have a single continuous film across the whole substrate, it's highly likely that it'll peel off, usually an hour or a day later. You actually get big flakes of the film just kind of coming right off. So it's totally unusable.
Their method definitely works, having a smaller cross-section. I also found that 5 nanometers of titanium underneath the copper is an effective adhesion promoter between the substrate and the copper. It probably does mess with the semiconducting properties a little bit, because now you've got titanium mixed in, but yeah, it was easier than trying to do kind of the pattern that they did. So 5 nanometers of titanium and then 80 nanometers of copper above it. Oh, and I guess I should mention why titanium. So there are certain metals like titanium and chromium that are super reactive, and they like to bond with oxides in particular. So they're often used as adhesion promoters in the industry. So you'll put a very thin layer of titanium or chromium underneath what you want to stick to the substrate, and it kind of acts as just an intermediate that bonds tightly to the silicon dioxide and then bonds pretty well to whatever metal you're working with and kind of acts as a glue. So that's why titanium.
If all goes well, we have a silicon substrate coated in mostly copper oxide. Now we need to deposit some electrodes on top so that we can test the photoresponse. The easiest architecture is called a metal semiconductor metal device, or MSM for short. An MSM device is basically 2 sets of interdigitated electrodes. This is a little different from a traditional photodiode, so I'll take a minute to explain. Most photodiodes are a PN or PIN junction. There's a P-type semiconductor placed next to an N-type semiconductor. The N-type material has an excess of electrons, while the P-type has a scarcity of electrons. To make it easier to talk about, this is usually referred to as electron holes. When you put an N-type next to a P-type, the electrons migrate from the N layer and fill up some of the holes in the P side. And the holes in the P layer migrate the other direction and combine with some of the electrons. The net result are positively charged ions at the border of the N region and negatively charged ions on the P side. This is called the depletion region because the charged ions produce a potential difference that inhibits electrons and holes from flowing across that region. It's depleted of mobile charge carriers in effect. Now, if a photon hits the depletion region, it can liberate an electron from one of those ions, forming an electron-hole pair. If we have this hooked up to a circuit, the electron and hole will migrate in opposite directions and generate a current, which we can detect and then amplify. So that's how a traditional photodiode works. But the device that we want to build only has copper oxide, which is a P-type semiconductor. We don't have an N-type material to pair it up with, so we can't actually build a PN junction. And that's where the MSM device layout comes into play. Instead of using 2 different semiconducting materials, P and N, we pick a metal that forms a Schottky junction with the semiconductor. In this case, aluminum has the right work function for our needs, so we'll use that. The Schottky metal takes the place of an N-type semiconductor in our device. The mechanism is a little different, but it also forms a depletion region when biased, so the net result is basically the same. Electrons flow from the metal into our P-type semiconductor and fill up some of the holes, leaving behind charged ions. But because there are so many free electrons in the metal, that when holes move in the opposite direction, they get swallowed up by the metal. So while a depletion region is formed like a PN junction, it only forms in the semiconducting material instead of being on both sides. Otherwise, it's basically the same. The charged ions in that depletion region inhibit the flow of electrons and holes due to the potential difference. And again, when a photon strikes this depletion region, it generates holes and electrons, which become a photocurrent. I went through this all kind of quickly, so if you'd like to learn more about all this, Projects in Flight just released a really amazing video walking through all of the underlying physics that make semiconducting materials work. I highly recommend checking it out, as well as the rest of his channel, because he's doing a lot of really neat semiconductor fab stuff right now. Anyway, practically speaking, MSM devices are basically 2 Schottky diodes put back to back. And being symmetric, it doesn't matter which way you'd bias the device. One side of the electrode will be forward biased and lead to a large current, but the other side will be reverse biased and rectify the current. And most importantly to me, they are single layer devices, which means we can pattern them directly on top of the semiconductor. So fabrication is pretty simple, which means the next step is to actually make those electrode patterns. To do this, I'm going to use electron beam lithography. I've made a video about this in the past, which you should totally go watch. But essentially, we're going to use a resist material that is sensitive to an electron beam, then scan a beam across the surface to develop a pattern. In the original video, I used acrylic injection molding beads dissolved in a solvent. My DIY resist worked okay, but it wasn't ideal and led to some problems. So to make things easier for me this time around, I purchased some real PMMA resist from a lithography vendor. I've also been working with the R&D team at Phenom to improve the Python API that controls my scanning electron microscope. The folks at Phenom have added a new patterning API, which offers a lot more control of the process and has helped immensely. So between these two improvements, I've been able to pattern some very small and pretty crisp electrodes. After patterning, we use a developer solvent to selectively dissolve the pattern. Then we put it back in the sputter chamber and coat with aluminum. The aluminum will coat the entire surface, but only the regions that have been removed in the developer will have aluminum touching the underlying copper oxide. It's basically acting like a stencil. Finally, we place the chip in acetone to strip off all the remaining resist. The only metal left behind is in the shape of our electrode pattern. This is called a liftoff process because we're physically lifting the metal off instead of using something like a chemical etchant to dissolve it. For liftoff to work well, you need a solvent to get underneath the metal and dissolve that in-between resist layer. However, this only works if the sidewalls of the resist remain uncoated with metal. If we have sidewalls that are sloped outwards, for example, the deposition process will coat them in metal just like the top surface, and there's no way for the solvent to get in and dissolve the underlying resist. So we need vertical, or even ideally inward sloped sidewalls. There are a few ways to do this, but in practice, the easiest method is with a bi-layer process. So I'm actually depositing first a layer of MMA copolymer, followed by another layer of PMMA. The MMA dissolves slightly faster in the developer, leading to an undercut region. This undercut is unlikely to get coated with metal and provides a location for the solvent to start dissolving. It's a little hard to make out, but here's a cross-section view of some tests I ran. You can see like a T or mushroom shape. The broader layer at the top is the PMMA, and the narrower neck region is the MMA. You can also see that in this particular section, the aspect ratio of the MMA layer was too high, and it actually fell over during development. This would impact the resolution of the feature you're trying to make, or maybe even lead to a failure, not allowing the metal to lift off. These types of failures are common until you find a set of parameters that work for you by adjusting the thickness or the electron beam dosage or the development time. There's just many, many variables to play with before you get a good, consistent process. But if all goes well, you should get a nice, clean liftoff and have patterned electrodes left behind.
So I forgot to mention that in these cross sections, we can also see the copper oxide layer really clearly. There's basically a single layer of large copper oxide grains sitting on top of the substrate. And this is really cool because it mirrors basically what the papers show, although the photos aren't quite as crisp as what's in the Nature paper. But yeah, super cool to be able to see this single layer of grains rather than really fine copper grains.
And now it's just time to test it with like a multimeter, right? Yeah, honestly, I wish. That would be a lot easier. But this brings up the next big problem in that we have micron-sized features that we need to probe. This is typically done with a specialized piece of equipment called a probing station. Probe stations are ludicrously expensive, even on eBay. But they are fundamentally just really simple devices. So instead of buying one, I built one myself by cannibalizing the head off of a microscope and bolting it onto a steel plate. Then I used these cheap XYZ stages, printed up some adapters to hold magnets, which attach it to the steel plate. The probe arm is just a piece of bent brass tubing, secured by another 3D print to the stage. On the opposite end is a sharp tip held in place with a small spring. Then the brass tube is soldered to an electrical cable, completing the circuit. The tip itself is a piece of tungsten wire that was electrochemically etched down to a very fine point. It's actually a really simple process. You just take some potassium hydroxide and apply a small voltage to the tungsten. Eventually, it will erode away and leave a sharp tip. Now, finally, it's time to test our devices. All right, I'm filming this on my phone just in case I can't get it to work again. I want proof that it actually works. So I'll get better footage of this in a minute, but I've got the sample on the stage, probed on the two electrodes under the microscope. And currently the light is off because it's sensitive to light. And so what we see on the curve tracer is basically an open circuit. Just a quick interjection here. In case you haven't seen these before, these are called IV curves or current voltage curves. The curve tracer will apply a variable amount of voltage plotted on the x-axis and record how much current is generated, which is then plotted on the y-axis. This can tell you a lot about the device and help characterize what you've actually created. So for example, an open circuit will have a flat horizontal line. No matter how much voltage you apply, no current will conduct. Similarly, a short circuit will have a vertical line, because it conducts electricity immediately regardless of the voltage. Here are a few other common devices. Resistors are a straight line with some amount of slope. Capacitors will form an ellipse or a circle of some sort, and transistors form a kind of hairpin curve. Diodes will have a horizontal component when the voltage is negative, and an upward slope when the voltage is positive. Diodes resist the flow of electricity in one direction, but allow current to flow in the other direction. So the curve is asymmetric with two different behaviors. And so what we see on the curve tracer is basically an open circuit. And there's a little bit of funky stuff going on there. But the thing that really is noticeable, if I turn the light on, which is back here, this does that. Look at that. Let's do this again. Light off. Takes a little while to reset. Light on. Off. On. How cool is that? Clearly not working quite how it should be, because I think the forward and the reverse bias should be identical. It should be a symmetrical device, and it is clearly not. But, you know, hey, we'll take it. Okay, one quick update. I think I might know what's going on with this curve. So the MSM electrode should be symmetrical, forward and reverse bias, because it's a symmetrical device. What might be happening here is that I've probed through the copper layer and hitting the silicon, in which case I might have created a PN junction or a PIN junction, because I've got silicon, silicon dioxide, cupric oxide, and then the electrodes on top. So it's possible I'm seeing the response of the silicon cupric oxide kind of interface rather than the MSM, which would give, I think, a more traditional forward versus reverse bias looking different. So as you heard there, after I got over my initial excitement, I did start to doubt the results a little. The curve looks a lot like a diode, which isn't what we want. Okay, quick update. I think this one's better. It looks a lot more symmetrical, and if I turn off the light, it looks a lot more like an open, and nicely symmetrical too, which is good. There's a little bit of, light in the room, which is affecting it, I think. But yeah, it looks pretty good. I mean, it doesn't look good. It's probably a pretty crappy device, but it is symmetrical, which I think is important here. And I don't know if I can show you. Oh, this is really hard. There we go. That's it. It's getting probed. So that looked better, but the whole thing spooked me a little bit. Remember what I said earlier in the video? It would be pretty silly to go through all this effort to make a copper oxide device and then realize we were actually measuring the silicon substrate instead. Yeah, well, I was starting to feel a little silly at this point. The probe tips are very sharp and very hard because, it's tungsten. So it's definitely possible that we scratched through that silicon dioxide layer and we're actually probing the underlying silicon. The copper oxide itself is really fragile, and the silicon dioxide layer is pretty thin, so it's not a crazy thing to expect might happen. In another test, I probed the bare silicon and the copper oxide, and the results look suspiciously similar. To resolve this, I decided to tackle it in two ways. First, we can just use a different substrate that isn't a semiconductor, like glass. It makes electron beam lithography step a little more complicated, but it entirely rules out any kind of interference from the substrate. Honestly, I should have just done this right from the beginning, but, hindsight and all that. So I tried using glass cover slips at first, but the furnace temperature is just hot enough that it makes the glass start to slump. So I had to switch to using fused silica, or quartz. Second, we can try and analytically determine if copper oxide was actually being grown. There are a few techniques that can do this, like Raman microscopy or X-ray diffractometry, but purely by coincidence, I was talking to a company around this time that was interested in sponsoring a video. They make a special atomic force microscope that can also capture FTIR spectra. So instead of just listing talking points at the end of the video, I thought it would be fun to actually send them a few of my samples and we could see, using their instrument whether we've generated copper oxide. One sample was oxidized at 200 degrees on a hot plate and should in theory be mostly copper 1 oxide. Another sample was oxidized at 600 degrees in the furnace and should be mostly copper 2 oxide. These samples were the main goal, but I also included a sample that was oxidized in oxygen plasma and another that was thermally oxidized using a laser. Laser processing could be really interesting for future experiments. The furnace oxidation technique is really effective and simple, but it's slow and difficult to integrate with other steps just due to the temperatures involved. In contrast, locally oxidizing with a laser is super fast and can be targeted to specific areas. So Molecular Vista makes a machine called the Vista 200, and it uses a really fascinating principle called photo-induced force to sense the chemical makeup of a sample with nanometer resolution. Many materials absorb infrared wavelengths of light. But importantly, molecules will absorb specific frequencies according to their physical structure. A carbon-hydrogen bond will absorb a different frequency than a carbon-oxygen double bond. By scanning a material with a wide range of infrared frequencies, you can generate a spectrum that tells you a lot about the chemical makeup of the sample. This is the basis of infrared spectroscopy, and is a technique that you might have done in a basic organic chemistry lab. But IR spectroscopy doesn't provide a lot of spatial resolution. Even if you focus the infrared light down to a small point, you're limited by the diffraction limit of photons. Mid-infrared frequencies can only be focused down to about 3 to 10 micrometers, which for context is about the feature size of semiconductors in 1971. Most modern devices have transistors sized in nanometers. If you're looking for organic contaminants or accidental oxides in your semiconductor process, traditional IR spectroscopy, well, it'll just really struggle. That's what makes the Vista microscope so interesting. It can collect IR spectra down to about 5 nanometers spatial resolution, which is clearly way below the diffraction limit. It does this by exploiting an optical phenomenon called the near field. A metal-coated probe is positioned near the surface of the sample. We're talking like within 10 nanometers of the surface. A laser is then focused on the tip and the sample. Photons are electromagnetic waves, so they will drive the free electrons in the metal tip, causing the tip to act as a nano antenna. This creates an enhanced electric field at the tip. This field and the infrared light will polarize the sample to form a charge on the surface. The mirror image of the sample's charge is then formed in the tip, so we end up with an attractive force between the tip and the sample. This dipole-dipole interaction occupies an incredibly small volume and can be sensed as a downward force on the AFM probe. Importantly, this interaction is mediated by the same mechanism that's used in IR spectroscopy, namely that different molecules absorb and resonate at different IR frequencies. So the Vista 200 works by scanning a tunable infrared laser across a wide range of frequencies, and then measuring the resulting photo-induced forces on the tip. The forces at different frequencies are then plotted to generate a traditional IR spectra. You get a chemical makeup like IR, but resolution like an AFM. And because it basically is an atomic force microscope, you also collect topographic data at the same time. The way it does both at the same time is by utilizing multiple resonant modes of the cantilever and modulating the frequency of the laser. It's a little too in the weeds to talk about here, but if you're interested in more details, I've got a link to a white paper describing how it works down below. Now, Molecular Vista warned me about potential sample contamination. I had to package up the samples in specific wafer carriers and only use acrylic-based metallic tape. The microscope is just so sensitive that it can pick up contaminants like silicones outgassing from nearby adhesives. Silicones and silanes are everywhere and stick to most surfaces, so we had to be really careful about sample prep and packaging to ensure that we got good results. But getting back on track, we have some preliminary results from the 200 and 600 degree sample that I can share today. First off, there's confirmation of a change in grain size as we'd expect. The 600 degree sample has considerably larger grains just by looking at the AFM topography. And this follows the results from the paper. We were expecting to see this. If we look at the IR spectra, we can see some differences as well. The 600 degree sample has an increase around 1460 and 1100, which according to reference IR spectra correlates with copper 2 oxide. And in contrast, the 200 degree sample has more signal around 640, which is indicative of copper 1 oxide. I'm still working with Molecular Vista to refine these results. They've actually requested some calibration samples from a collaborating university, so that we'll have some spectra from a real university lab to compare against. I don't think the results will change much, but it might let us differentiate how much of each oxide is present in the samples. It's likely that both samples are actually a mix of the two oxides to varying degrees. We also started to analyze the laser oxidized sample and one that showed more complicated pattern structures, but due to deadlines on my end, we're still collecting the data and it's not quite ready to present yet. So I'll save those for a future video. So while the results are still preliminary and we're working on the rest of the oxidation tests, I think they're pretty suggestive that we've generated not just copper oxide, but the desired copper-2 oxide. Which means it's time to start over and rerun the whole procedure on our quartz wafers. Depositing copper, oxidizing in the furnace, patterning, developing, depositing aluminum, and finally the liftoff. And when we probe it, okay, so the curve isn't quite as impressive as before, but it's very clearly photosensitive. And there's no chance an alternate semiconductor is interfering with the results. When the flashlight is on, the current is definitely increasing, especially at the higher voltages. It's technically possible something funky is happening between the probe metal and the copper oxide, or it's just a simple photoresistive effect, but given the shape of the curves, I feel like we're seeing a legitimate metal semiconductor metal device. While testing, I also accidentally blew up a few devices.
That film's wrecked. All right, that one's done. All right. And I think I lost it. Oh, it went. So 100 volts was too much, apparently.
Oh, that destroyed it.
Yeah. Totally wrecked.
It took me a while to figure out like what the hell was going on because the curve would just suddenly turn into an open circuit while I was testing. I'm still not entirely sure, but I think my curve tracer accidentally emits like a big pulse of current when changing settings, because I noticed the devices would sometimes fail when I was fiddling around with the knobs. Looking under the microscope, you can see the traces physically blown away. You can trace the exact path the short circuit took, from one electrode to the other, leaving behind molten bits of material. I think the oxide was probably heated up rapidly due to internal resistance, and then reaches a critical point where the temperature is hot enough to melt it. This allows more current to flow, propagating the effect, resulting in, basically, a molten short circuit. Alternatively, and this is kind of a fun idea, it might be like a tiny thermite reaction. After all, we have a very thin layer of aluminum sitting on top of copper oxide, and we're heating it up with electrical input. It has all the ingredients of a copper thermite reaction. Not really sure, but it makes some really cool images. I even managed to catch one of these on camera, although unfortunately it happens so fast that it only occurs on a single frame of video. Now, I honestly should have just stopped here and made the video, but I really wanted to make a functioning device. So I designed a 4x4 array of pixels and electrodes to sit on top, and then started to redo the whole process to fabricate it. Unfortunately, this uncovered a lot of new issues, mostly related to stitching multiple fields of view together, process reliability over such a large area, and many more avenues to slowly lose my sanity. So we're going to save all that for a future video. But I just had to test some part of this device, even if the whole thing wasn't functional because of the misalignments between the fields. So if we very carefully probe two small parts of this array, we can see a nice little photo response here too. Which makes me hopeful that I can get this whole thing working and have the world's crappiest DIY camera sensor.
Cool. Do I go to 400 volts? That seems like a bad idea. Oh, that destroyed it.
Okay, well, I hope this was interesting to you because it absolutely erased a few years off my life. I've started updating my control software to incorporate machine vision for better alignment and tweaked how I manage backlash of the physical motion stage. I think the next few tests will be a lot more successful because of these changes. And with luck, we'll have a working 16 pixel camera before the year is out. Fingers crossed. And maybe a more advanced design after that. I don't know, we'll see. Thanks again to Molecular Vista for sponsoring this video. It was fun to have a sponsor actually contribute to a project with real data instead of just talking points. So if you're in the market for an AFM that can also resolve FTIR spectra with spatial accuracy of nanometers, make sure to check out their instrument and request a demo. I think that's all I've got for you. Thanks for watching, and I'll see you next time.